There we go. All right. So my background is in fault mechanics, earthquake source mechanics, and seismic source theory. I tell the industry I'm a geophysicist, given all that. And when I first started looking at these high frequency vibrations, drilling vibrations 6 or 7 years ago, I say, you know, it's pretty tough for the industry if you're a geophysicist and you have to process drilling vibrations, you know, to get by in the industry. Well, things haven't gotten any easier. When I first started with this, yeah, when I first started,
Wait, no, it's not on.
okay.
Okay, we're good.
Okay, guys. So, all right, I'm not gonna. You guys don't want to start over, right? No. Okay, good. All right. So when I first started looking at these high frequency vibrations, there's only one vendor in the industry at the time, 6, 7 years ago, that had a continuous 1 kilohertz sensor. That was NOV. They're running the PDL tool at the time, and now there are multiple vendors. Halliburton's got their Cerebro tool. The Sambian group, the Scout Downhole, has got a sensor. Baker's coming to market with the multi-sense, probably 2.0. Group out of Edmonton that used to be with NOV called Sensient Tool, they have a sensor. So there's now a lot of new data out here with the vibration data. And the question is, you know, what can we do with these measurements to better understand the drilling process? What can we do with these measurements to try to maybe answer some of the questions around that we're talking about here today, bit design and things like that. So my outlines, I'm going to talk about two things. I'm going to go back in time a little bit and look at a phenomenological model of the drilling response. And then I'm going to look at some lab data with some of these vibration measurements. I'm going to click here.
It's not, yeah.
Yeah, those aren't working either. Yeah. Oh, there it is. Yeah, I've been.
Click on the screen.
Oh, click on the screen. Okay. All right, cool.
Now it's going to work.
Okay, thank you. All right, good. All right, thank you for live now. So, all right, so a phenomenological model of the drilling response. So when I first started looking into this, again, it was about 6, 7 years ago, one of the models that really caught my attention was this model published in 1992, where people are looking at the specific energy of drilling against the drilling strength. And what this does is the linear model, and it predicts the relationship between these two variables. And the nice thing about this is that you can predict the drilling response in terms of these two energy inputs along this friction line here. And the other line here that we're looking at here is called the cutting line. And so where those two lines intersect is the cutting point. So all your drilling response for efficient drilling should be to the right of that line and on that friction line. So this gives us a way to quantify the drilling response based on this. And this model is very simple. It's robust. It depends on a couple of rock property parameters. Looks like a coefficient of friction, an intrinsic specific energy of the rock, and then a couple bit constants. And the laboratory experiments that these guys published more recently in 2009 show you can see that the data points here fall along that line. Let me try to see if this, yeah, the data points here fall along this line. And notice when these data points here fall off the line. So as you get to increased drilling strength, right, and come off this line, it means you're losing less energy to frictional processes. You're actually drilling more efficiently. And so this is a good way to take these aggregate measurements of weight, torque, RPM, ROP, put them through a model and allow us to understand where I'm cutting efficiently or not. So as we all understand, to put more weight on, I get more efficient cutting conditions. Okay, so we've heard a lot about vibration measurements at the sensor, high frequency. You know, how are we going to bring this into the conversation? You know, weight on bit, torque on bit, RPM. They've been around for a long time, probably since they first started drilling. This is how we drill. These are standard inputs into the drilling system. They've been shown to predict linear constraints to response to PDC bits. So We know that they're predictive in terms of model response and way to understand drilling efficiency and drilling dysfunction. We can modify these variables in predictable ways to increase drilling ROP and decrease dysfunction. Everyone knows what they're doing with these measurements. One of the things that's interesting though is that these diagnostics, even looking at specific energy versus drilling strength, you tend to combine angular and linear motions. I don't have an issue with that per se, but what that means is maybe it's confusing a little bit about what we understand about the rock properties when we talk about frictional strength or intrinsic specific energy if I'm mixing these modes together. The other thing that's a little bit tough is ROP tends to be taken from the surface, which once you sync up, you can average it in and it's okay, but still it's not exactly. There's some inaccuracies in that. MWD data, the accelerometer data, it's niche. It's typically handled by in-house scientific experts. You don't see it offered commercially very much. Takes geophysicists like me to come up here and talk about it. The sensors are cheap. MEMS sensors are cheap. You can put multiple placements out there. You can put them on the collar. You can put them in line. And the other thing about accelerometer data too that weight and torque don't necessarily speak to is that they directly capture lateral motion. And so that's actually something that's kind of unique with the accelerometer measurements. You can get linear modes above motor. Above motor, things get a little bit more confusing. But overall, I think the real issue with the accelerometer data is they've always been difficult to quantify. So what we want to do is talk a little bit about today is how we're going to go about doing that. So we went into NOV's PDL facility up in Conroe. And again, thanks to NOV for allowing third-party access to that facility. And we did a series of step depth of cut tests in there, and I want to talk about some of the publications on the results of this measurement. So what we want to try to do is we want to try to understand how we would build a model to quantify accelerometer measurements. And so we took a couple rock types, a limestone, and we took granite. We took two different bit types. And because a lot of the effect of the model depends on the ability to accurately estimate those bit coefficients, the one we really said, let's look at the back rake angle, let's do some bit aggressiveness and see if we can't see some sensitivities there. But turns out you can't really just change one parameter on a drill bit very easily. If you change back rake angle, maybe you got to change something about your blade, maybe you got to change something about your cutter diameter, maybe change something about your cutter density, your hydraulics. It's all kind of interrelated. So at the end we said, change everything. And these are the two bit types that we got here. You got a 5-bladed bits, more of a nose cutters, bigger choppers, 16 millimeter cutters, and you got higher cutter density, smaller cutter diameters. I think those are 13 millimeter. You see some backup cutters, and that on bit B. We drilled two non-reservoir rocks. We drilled a granite, we drilled a limestone, and we calculated those properties. So let's not forget about the cutting conditions that we're working with here. Obviously, this is kind of a very unique case. Like the NOV guys are showing off their skills. They're in the laboratory a little bit, fished out some of those chips for us. Been artfully arranged. I actually don't know if those chips are arranged in the right way there with respect to that. What we expect from a bottom hole cutting pattern, but anyways, that's our interpretation. Okay, so one of the things that we talked about here originally, the original phenomenological model, is that those are strength properties. Friction is a strength property. Intrinsic specific energy is a strength property. Yeah, I'm talking about elastic properties, Young's modulus and Poisson's ratio. There's been some recent publications out there. There's some laboratory data from a group out of Edinburgh that showed a drilling hysteresis effect. And again, a group drilling pre-salt out in Campos, again, showed drilling hysteresis using some of these high rate sensors. So I think we're starting to see some physical evidence for an elastic response to the rock, but let's just take this at face value here, not worry about what those two terms mean, whether or not they're elastic or strength or whatever they are. What I've done here is shown a linear relationship between the accelerometer inputs. That is, I have an axial acceleration and a lateral acceleration, and it's related by a slope and intercept with a couple bit coefficients. So conceptually, it's the same sort of way of thinking about it as a phenomenological model that was developed back in the 90s. Okay. And we want to talk a little bit about conventions here too, because what we see is you know, with the lab experiment we had a 2 collar mounted arrays, 2 collar mounted accelerometers. And the nice thing about that is you can't separate angular and linear motions unless you have 2 accelerometers. And so with some simple math, here we can calculate the lateral mode and angular mode. So what we're talking about here, this is a linear motion, this is a linear motion, and this is a linear motion. So we're comparing linear motions with linear motions and looking at a linear relationship between these 2 variables. And this is what we're trying to do, is can we quantify the joint response using this model? Yeah, I know, I got too slow. So I'm talking. So we drilled about 60 inches of rock. This is our stepped up to cut test. Went from 5 to 40 kilopounds on weight, RPM between 90 and 150 RPM, and you get the reactive torque there as well. And so obviously we see a nice relationship between the RMS, the axial acceleration, and then the weight on bit. Obviously at lower weight on bits, there's less transmission axial acceleration. That relationship breaks down. As you start to put more weight on the bit, you start to knock down on the axial accelerations at higher weights. I'll spend a little bit of time on this slide. I know I'm running out of time, but this is a 1 kilohertz bandwidth. So this is 2 kilohertz sample rate. And what we record on the collar mounted arrays, okay, is there's a torsional channel and the radial channel. That's actually measuring the field of the collar mounted arrays, okay? But when we decompose these into a linear motion and an angular motion, we see that the torsional channel is picking up mainly angular motion, especially between 100 and 300 hertz. And then we can see the linear motions quite clearly defined on the radial channel. See example of bit whirl right here. So low weight on bit, 5 kilopounds, spin it up to 150 RPM. That bit A, the more aggressive bit, loses stability in the limestone. You can see a very clear example of whirl on your frequency. The other thing is, again, you start to see the energy increase. Linear modes out here in the higher frequencies, about 300 to up to 1 kilohertz, dominated by a torsional mode between 100 and 300 hertz. This used to be, when I first started this is called bit chatter. So anyway, so we use this linear model, we process the data, and these are the sort of the slope and the intercepts we get. So based on, again, conceptually with the phenomenological model, you can see, again, a very narrow, flat response here in this curve, a little bit more noise on this curve here, and then same thing here at the granite. Bit B, again, a more stable response with higher cutter density in the backup cutters, a little bit more of a shoulder response. Again, a little more stable, curves aren't quite as noisy as bit A. And again, so over 5 to 40 kilopounds with 2 different RPMs, we're showing that we get a nice linear model to our drilling response with the accelerometer data. Okay, so instead of using weight and torque, RPM and ROP, just using accelerometers, we can be predictive. And this is a statistical description of that. Again, you can see the actual 7 MPSI for the Youngs, 9 for the Limestone, and these other terms here. And for the most part, between 5 and 40 kilopounds, we're getting a pretty good stable estimate of those rock properties. Again, you get down to low weight on bit and high weight on bit, you start to see some deviation. So this is nice, consistent measurements. Maybe we can understand something about the drilling efficiency here. Again, the results for bit B, again, very, very similar. Maybe it's very hard to get high weight on bit measurements in these laboratories. You get maybe 10 or 20 turns of the bit before you've gone 4 or 5 inches into the rock.
Were the bits buried in the rock? Was there already a pre-existing sort of pilot hole that the bits were in?
Yeah, we spent some time working on that bottom hole pattern before we started to apply the weight. Yeah, and so they were probably about 1 foot or 2 feet into it. And then obviously spent some time carving out the bottom hole pattern, apply the weight, and then away you go. Yeah. All right, so I guess the big deal here, what I wanted to show to the community today was that we had 2 very different PDC bits out there. We were able to process them and analyze them both the same linear model, okay? Obviously, it's controlled laboratory conditions. There's no mud, there's no pressure, and so on and so forth. The other thing is, just like with the phenomenological model, obtaining the bit constants is key to either method. So I'm gonna stick around today because I want to understand if there's, as I said, these data streams are coming out, right? We got 5 vendors offering high frequency drilling vibrations into the community right now. What can we do with them? How can we use these data to understand better rock working diagnostics? So, and thanks for your time.